Alright, for today's video we're going to actually do some proofs of some basic differentiation rules, and then we'll use those shortcuts, or we'll use those as shortcuts to do several derivatives in a row very rapidly. So this is not in the notes packet, this is a separate page, but I really would like to see this as a page of notes. So go ahead and pull out a blank sheet of paper to do this on. The first thing we're going to do is we're going to find the derivative of a constant. Now visually, if you think about what does the graph of a constant look like, it's just a horizontal line. And so it makes sense, at least to me it makes sense, that at any point the slope of the tangent line should be 0 because it's a horizontal line. So I believe the conclusion is the derivative of a constant is 0. But we're going to prove that. So using the formal definition of the derivative, the limit as h goes to 0 of f of x plus h minus f of x all over h, this is equal to our derivative. Now the function at some arbitrary x value plus a distance of h, what does that evaluate to? Well, there is no variable in this expression, so there's nowhere for x plus h to be plugged into. So the value of f of x plus h is c. Likewise, the value of f of x is also c. And if we take the limit of this expression, we are asking what is the limit of h going to 0 of 0, because c minus c is 0, 0 divided by h is 0. And then when we do direct substitution, 0 in to the h value, we get an answer of 0. And this supports our statement of the derivative of a constant is 0, which is what we believed. Now when we look at that in the notes packet, this is what we've established, that if we have a constant function at any value, the slope of the tangent line will be 0. So if I ask you, what is the derivative with respect to x of this constant? I get an answer of 0. Again, this is another notation for derivative. Here I have the constant 45. The derivative of s would be s prime. The derivative of a constant is 0. Here I have f of x. The derivative of f is f prime. And 0 is a constant, so the derivative of a constant is 0. The last one, it almost looks like there's a variable because there's this k, but we're assuming that k is some arbitrary constant times pi halves. So the derivative of y with respect to x, which is all that we've really seen, is, well, the derivative of a constant is 0. Alright, that's our first proof. The derivative of any constant will be 0 because everywhere on a constant line the slope is 0. Okay, moving on to the next differentiation rule. The differentiation rule that we're exploring here is a single variable. So in this case, f of x equals x. Or we could say, you know, like s of t equals t, if t was our variable. Or g of t equals t. We know visually that this graph is the identity function. And if we were to draw that graph, we would get a line that is sloping upward at a slope of 1, rise 1, run 1. So by that logic, I would argue that the derivative should be 1. And let's go on and prove this using the formal definition of the derivative. The limit as h goes to 0 of f of x plus h minus f of x over h is equal to f prime of x. And we want to evaluate this expression for that function. So we're going to go ahead and do that. F of x plus h means plug x plus h wherever you have a variable, and we have one variable here. F of x means plug x in wherever we have a variable, so we have that one variable. And this is all over h. If we were to simplify this expression, x plus h minus x in the numerator is h, and we still have that h in the denominator. And h over h simplifies to 1. And now when we evaluate the limit expression, if I plug 0 in for any h's, I arrive at a value of 1, which supports my belief that the derivative was equal to 1. So the derivative of any single variable is 1. And when we consult our notes on this, well, let's draw what we've drawn. We see that this slope, wherever we're at, the tangential slope should be 1. So what's the derivative of x? Well, f prime of x equals 1. If our variable is t and we're taking the derivative with respect to t, then s prime of t equals 1. Here our variable is t, and it's a singular variable by itself, so x prime of t, that's our function notation with a prime, the derivative of t is 1. Two very basic rules that pop up pretty often. They're basic rules. Okay, for this next proof, you're going to have to take what I say with a little bit of just belief in what I'm arguing. If you want to explore it more in depth, I'm more than happy to talk with you individually. But the idea here is we want to find the derivative of x to some power of n. And if we use the formal definition of the derivative, we can do this. Where this falls apart for us, at least in this presentation, is when n becomes a larger and larger number, evaluating f of x plus h becomes a bit of a challenge. But I'm going to show you a pattern, and hopefully from that pattern you will be able to deduce what's going on. So here's our f of x plus h, so the variable to the nth power, minus f of x, the variable to the nth power, over h. And as a sidebar, I want to show you a couple quick expansions. I'm going to write them out here off camera and then discuss it. So here, I'll pause this right now. Okay, so there's this pattern that gets established as we distribute or FOIL our expression here. We're pretty familiar with the quadratics expanding into something that looks like this, and a few people may have even gone to the third power and gone through the process of expanding it, x cubed plus 3x squared h plus 3xh squared plus h cubed. I put a dot 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 here because I want the pattern to be clear to you. If we keep going up, the next one would be the fourth power would be x to the fourth plus 4x to the cubed h plus, and then there's some more things in here, plus h to the fourth. And I'm leaving these out here because you're going to see them cancel in a short bit. So the pattern that we should be seeing is the very first term is always x to that number, and the next term is that number x to a degree less. So 4 minus 1 is 3. So if I have x plus h to the n, my first term is going to be x to the n. My next number is going to be n times x to the n minus 1 times h. And then there's all these things that happen in between. Now, the reason I point that out is because when we expand this polynomial, this expansion here is going to become x to the n plus n x to the n minus 1 h plus a whole bunch more all the way until we get to h to the n. Subtract f of x, which is x to the n, over h. Now, the reason I didn't write out all of these is because it varies based on what the n value is. But you'll notice that x to the n cancels with that x to the n. Furthermore, there is now an h in every single one of these terms. So if I were to factor that h out, we could see that the h cancels out of the numerator and the denominator. Now, all of these terms that I have not written have an h in them. So when I evaluate the limit, plugging 0 in for h will make all of these unwritten terms equal to 0, because a number times 0 is 0, or 0 up to an exponent is 0. So all of these terms cancel out, and we are left with n times x to the n minus 1. Now granted, this is an atrocious proof that I imagine I only got a few of you to deeply understand, but that's okay. I just wanted to show it anyways. What's really cool is we never have to do it again, and instead we have this shortcut rule. When I have x to the n, the derivative is n times x to the n minus 1. And that's going to be our most frequently used derivative rule. And so we're going to see that right here. It's the power rule. This is the expression for it. Taking the derivative of x to the n is n times x to the n minus 1. So what is dy dx in this case? Well, the n value is 2, and 2 minus 1. Or if we wanted to simplify that, just 2x to the first. So what happens when we find the derivative is the exponent drops down in front, and then we decrease the exponent by 1. And it doesn't matter whether the exponent is an integer or a fraction. In this case, this rational expression has a fractional exponent. So if I wanted to write the derivative, well, the exponent drops down in front, and we decrease the exponent by 1. Okay, now in this case, this expression could be simplified a little bit further. We could write this as 1 over 2 root x. But that's an algebraic manipulation, not a calculus one. Okay. For this one, g of x, this is the same thing as saying x to the negative 1. So if we take the derivative of that expression, the negative 1 drops down in front, and then we decrease the exponent by 1. And this again, once we've done the calculus, we can use algebra to simplify this expression to be negative 1 over x squared. Very similarly in part E, if we write this as a exponent, we could write this as x to the negative 2, and when we take the derivative, the negative 2 drops down in front, and we decrease that exponent by 1. This expression here can be simplified to negative 2 over x cubed. And finally, the last one, if I write this as a negative exponent, then I can apply the power rule. The power rule says drop the exponent down in front and decrease that exponent by 1. So negative 2/3 minus 1 is negative 5/3, which simplifies to negative 2 over 3 cube root x to the 5th, if we wanted to write it in radical form. All right, so that was a lot for this video, so I'm going to stop the notes on this and we'll pick up more on the next day. But this for sure is the one that we're going to be using the most. And don't worry about deeply understanding the proof. It'd be awesome if you understood the proof, but now we have shortcuts, and we're going to start using shortcuts more and more. Thanks for watching. Have a good day.